escaped out. He just okay. It was like whenever he had COVID. He's fine. He just wanted to leave.
Here we go. So, real quick,
strange boy.
The best news to come out of last night was they stacked the nose cone on the Starship down in Texas. Now it's like a full Starship that's gonna it probably launch in the next couple weeks. So. Yes, like it's in like gonna go to the moon. Not the moon. Well, this one might go to the not this one, but it'll go to the moon and to Mars. So.
Johnny, you ready to not run?
What?
I sure hope so.
I sure hope so too.
Bro,
there's no way they can make this go out there. What if they made us?
But that means.
What?
Bulldog makers and
The moon, it only takes like 4 days to get so many.
They probably just wrote a bunch of
This one's not going.
We can't even walk
That's the thing. It's gonna go like
We can't leave the building if it's like this.
I guess
Yeah, but it's clearing up.
I want there to be a permit.
Huh?
I don't have to go around.
Whoa, right there.
Yeah, that was a choking cough, not a COVID.
Or like as soon as the bell rings, it's the biggest thunder strike. Just
Yeah, I know. Like we just need like a tree on fire or something.
Let's see.
We need some lightning to like straight up strike a person. I'll volunteer. I'll walk out right now.
Thank you for the team, but
Do it for my teammates. I love my teammates. Take one for the team. Get electrocuted.
It'll probably go to the field now.
Okay, now I got that signed. Let's go there. No, I got better. Yeah, I've already voted. All right, so what we're doing today, we're doing another one of the explorations. A couple of y'all didn't submit your questions for the last exploration, so the video's up on Google Classroom, and you can do that. So we're gonna go through it again today. We're gonna go through the same kind of thing that we did. I'll kind of talk about all the answers, and if you follow along, you should have a pretty easy grade to do. So make sure that you're following along. If you get behind or you're not to the same page that I am, let me know, and I will get you set up on this. So go ahead and log in. Yeah.
The same one from yesterday.
No. First off, yesterday we didn't do an assignment. I lectured yesterday. Not yesterday, no. Yesterday we did just a lecture. I talked about the radiometric dating, the absolute dating. The day before that we did the relative dating exploration. So we're going to do the absolute dating exploration today. Go log into Discovery Education. Click on the assigned reading. It's just a reading, so it's not going to take you to the actual assignment. For whatever reason, they won't let me assign these. I can assign the one that has a paper answer sheet, but I can't assign the one that actually has the full answer sheet. So click on the reading, which will take you to the Explore tab. Click on Explore More Resources, and it takes you to the tab that has a bunch of assignments on it. Go all the way to the very bottom and click on Assess, and open up the Exploration Absolute Dating. It should open it up in a new tab, or I think in yours, either a new tab or a new window. Mine, it opens up in a new window. And we're going to go through this. So, first off, it tells you that absolute dating is a technique that is used to determine the specific age of an object in years. So, not just older or younger, but it tells you the actual years. It involves a physical or chemical analysis of the object that can be used to calculate the absolute age of the sample. Radiometric dating, which is where we use the radioactive elements, is a method of finding the absolute age of a rock or fossil using measurements of decay to form daughter atoms at a specific and unchanging rate. So your original radioactive element is called the parent atom. So that's what you start off with. Our example that we used before was uranium. And uranium is unstable. The nucleus will spit out different parts of it, either alpha particles, beta, or positron particles, and it will slowly turn into a different element. For something like uranium, it will slowly turn into lead. And so we look and see how much uranium we have left versus how much of the daughter atoms we have, which is lead. So uranium would be the parent atoms, lead would be the daughter atoms. And that rate that happens at is very specific for every single radioactive element, and it doesn't change. It always stays the same. It doesn't matter where you find uranium. Uranium will have the same half-life for that specific isotope. So the ratio of parent to daughter atoms in a sample reveals the amount of time that has passed since the rock or fossil formed. Parent and daughter isotopes, along with other important isotopes, can be counted using an instrument called a mass spectrometer. So that's what we're going to do today in the lab. We're going to get ages of things based on the mass spectrometer. So it tells you to get familiar with the apparatus using this exploration. You can go in here and read about the experimental setup. So they have the entire setup here. And then up top, you can click on mass spectrometer, and it talks about how the mass spectrometer works and how they take the readings of this. We have a limited amount of time here. This isn't like block schedule where we got a bunch of time. We got 45 minutes. So we're going to keep going, and you're going to click on the Find Age tab down here at the bottom. So when you click on the Find Age tab, it pops up and gives you some instructions. It says, find the absolute age of the samples shown. 1, select a sample to place it in the mass spectrometer. 2, click on a radio button to select the appropriate parent isotope. And the thing to remember here is when we get there, carbon-14 only works in stuff that was living at some point in time. So like trees, animal fossils, something that has to be living to be able to use carbon-14. So if you're going to click on an animal fossil or like a tree trunk or something like that, you can use carbon-14. If it's a rock of any type, you have to use a different type of radioactive element, like uranium or plutonium. I can't remember what's up here. I looked at it earlier, but I don't remember which one you have. So click on the radio button to pick the actual radioactive sample. Click Show Half-Life or Show Information for more information about each one. Click on Measure to measure the parent-daughter ratio of the chosen isotope, which should help you figure out how many half-lives it's gone through. Click on Proceed to use the parent-daughter ratio to determine the absolute age of the sample. So by that point, you should know how old the sample is. First, calculate the percentage of the original parent isotope atoms that still remain. So is it 50%, which would be 1 half-life? Is it 25%, which would be 2 half-lives? 12.5 would be 3. Remember, it just keeps going down and down and down. So I'll read all this real quick. You have your chart. You start off at 100%, and then after 1 half-life, you go down to 50%. After 2 half-lives, you go down to 25%. After 3 half-lives, it just cuts that in half, 12.5%, and it just keeps going on from there. Let's see, 5, we already went through 5. Next, drag the yellow pointer on the graph so that it has a Y value that matches the percentage of the original parent isotopes that still remain in the sample. The corresponding value on the X-axis is the age of the sample. Finally, click on Check to check your answer and receive feedback about whether you got it right or not. So here's what we're going to do. You have several different rock types. You have a human skeleton in here in a cave. This, I can't see it super great. This looks like a little fossil up here at the top. You've got a piece of wood down here in the bottom. You have another, like an animal skull down here. And you have an igneous intrusion down here to look at. So there's lots of different things you can click on. Let's start with the human body. Human skeleton. This is not a rock. It's actually a living thing, or was a living thing. So I'm going to use the carbon-14. Oh, wait. So it puts the human skeleton sample in the, now I already forgot the name of it, the mass spectrometer. Now you click on your sample, carbon-14. You click Measure, and it's going to tell you the parent-daughter ratio is 3. So this is, let's see if the parent-daughter ratio is 3. So that means you have, what, 3 to 1? No, surely not. 1 to 3. Note that actually we would not be able to measure the amount of daughter N14 because this is gas that escapes from the sample. Instead, we would compare the properties of the C atoms in the sample to C14 proportion of the atoms B. So I think what they're doing here is they're saying that this ratio is the parent-daughter is 1 to 3. So for every one parent, you have 3 daughter atoms, which would make sense because you wouldn't have anything like above 1 to 1. So I think they're just going to give you the number on the right. So 1 to 3, is that going to be like 50% or 25%? You have to remember that with ratios, they don't give you the total. So like with a fraction, like 1/2 or 1/4, the bottom number is the total, not just one of each side. So here we have 1 for every 3, but it's a total of 4. So 1/3 should be, I believe, 1/4, unless I'm wrong, which we will see very shortly. So you click on proceed because you have the parent-daughter ratio. You click on proceed, takes you to the chart. You're going to take your little yellow dot and slide it down, I think, where you think it needs to go. Or do you click on it? I'm not allowed to do that. Oh, maybe you click it over here. Select the percent of the parent isotope remaining in the sample. If your parent-daughter ratio is 3, maybe is it 75%? That might make sense.
No.
It's not 75%?
No.
All right. So then it's 45%. Step 2, percent of the parent isotope remaining. Am I supposed to change that? That's not right. Check. That's not right. Is it 75? Hold on. The percentage. So you got to change the percentage, which I can't do from here. Let me come back here. I think it's going to be the 75%. Percent of parent isotope remaining. No, I can't change that.
You have to change it with the dot.
No, you are supposed to switch. You are supposed to drag this down.
My job,
I guess I couldn't do it with my pen from up
not
there.
that property.
Slide it down to 75. Check that. Yeah, so it is 75. I actually had it backwards. It's 3 to 1. So 3 to 1, which is not even going to be 1 half-life, because I still have 75% of the parent remaining and 3 for 1 of parent to daughter. So it's not even going to be 1 full half-life. You actually have to go less than that. So the full half-life is 5,730 years. And then they tell you this sample is about 2,375 years have passed. So it's not quite that old yet. All right. Let's see. Select another sample. So you can go through and do each of these. We can go to the skeleton of the animal. Put it in. Select carbon 14. And then measure. It's going to tell us that it's 0.25. Now we have like a fraction here. So 0.25 is equal to what fraction? 1/4, which would tell us it's how many half-lives? 2 half-lives. And so when you go to proceed, you just drag this down. I don't know why it's not letting me drag this down from up here, but it should be all the way down to 2 half-lives. I can't even do it from here. I guess you got to select this one first. So it would actually be 25, but it's come down to 20. And that should be right. Yeah. Technically, it should be 25, but So you can sample all these. Let's do one of the rock ones and see how old that one is. Select another sample. You have a meteorite, granite, or gneiss. Let's do the meteorite. That'll be the oldest. The meteorite, let's pick the rubidium, which is 49 billion years. Measure that. Your sample has a parent-daughter ratio of 15 to 1. So proceed. So 15 to 1. It's probably going to be the highest one, like 93% left. Scroll that down to 93. Oh, get in the right spot. There you go. That's close enough. Check that. So that's telling me that the meteorite's like 4.56 billion years. So pretty close to the age of the universe. I don't know if they need us to do all these to answer the questions. So let's go ahead and look at the questions and see what we get from the questions here. So we scroll down. How many questions do we have? 10 of them. Nice. And y'all, I guess I have the same thing y'all have. So they're all in the same one. You don't have one set of questions and then another. So explain what the half-life of a radioactive isotope is and why is it important to absolute dating. The half-life is the amount of time it takes for the radioactive isotope to decay into a different, more stable isotope. So if it's carbon, it's decaying into nitrogen. If it's uranium, it's going to decay down into lead. So the half-life is the actual amount of time it takes for half of your radioactive isotope to turn into a non-radioactive isotope or a more stable form. What?
Wait.
You all right? You got a question?
No.
Huh.
That was number 1?
Yeah. Yeah, so what is the half-life? The amount of time it takes for half of your radioactive isotope to turn into a non-radioactive or more stable element. Now, describe how the mass spectrometer is used for absolute dating. They actually will tell you about that here in the apparatus. You're on mass spectrometer. Basically, what a mass spectrometer does, you put a rock or a sample in here, and it breaks it apart and tells you what atoms it has inside of it and what percentage it takes of that. So it'll tell you how much of your sample is the radioactive uranium or how much of it is the carbon-14. So you can use that information. It's not going to tell you straight out, but you can use that information to figure out that ratio of your radioactive stuff to your non-radioactive parent or daughter atoms. So you can figure out what the half-life is. So it's kind of like right here in the second one. The mass spectrometer detects different isotopes based on their atomic weights. There are many different types of mass spectrometers to use for different purposes, yada, yada, yada. Yeah, basically it takes your sample and breaks it down and gives you a readout of what atoms are inside, what their weight is, and you can figure out what they are, and you can get that ratio to help you figure out how many half-lives have happened. Why is it important to consider the half-life of an isotope, the relative age of a sample, and the composition of the sample when deciding which isotope used to date a sample? All right, so they're kind of asking three different parts here. Why is it important to consider the half-life, how long it takes for an isotope to radioactively decay? The relative age of the sample, how old it is, and the composition of the sample. Because not every type of sample will have the same kind of radioactive element in it. So like your skeleton isn't going to have uranium in it. It's only going to have carbon-14. So if it's a living thing, you need to use carbon-14 to help you finish up this sample or to help you date the sample. If it's like a rock, like if we go back to the example here, you have rocks that are aged very differently. The meteorite is going to be very, very old compared to like this igneous intrusion or this granite over here. So for the meteorite, we want to use the one with the highest half-life or the biggest half-life because that's going to give us the most accurate reading. Where if you take a really old meteorite and use a radioactive element that has kind of the same age, there's not going to be any of it left. You got to make sure that you use the right one. So some things don't have certain radioactive elements in them. Other things, you have to make sure that there's enough radioactive element left for that age to actually answer the question that you're trying to answer. I know that's not really a straightforward answer, but it's not a straightforward question. So why is it important to consider the half-life of an isotope? Because you want to pick the right isotope for the right sample that you're trying to date. The relative age of the sample, kind of the same thing. You need to know how old the sample is and what your half-life is. That's kind of the flip side of the same coin. And then the composition, because some different samples aren't going to have the right radioactive isotope in it. So if you pick the wrong one, you're not going to get any reading, and you're not going to have any data to look at. So number 4, this exploration is about absolute dating. Get feedback on all the dates. Say that the ages are about a certain number of years. Why doesn't the feedback state that the age is exactly a certain number of years? Because there's uncertainty. When you talk about times that are that far back, you're not going to be exact. In most science, unless you're talking about mathematics, there is some sort of uncertainty. Either your tool's not that great, or even if it is great, it's still not perfect. The sample that you get isn't perfect, and with radioactive elements, it's all kind of random as far as how it decays into something else, and so there's a little bit of uncertainty there, and so that's why we don't give you an exact date. We give you this kind of range from a certain number of years to another number of years, which is why in the elections sometimes the polls are wrong, because even though they ask people, you don't ask everybody, and some people lie or tell you a different answer or are uncertain. And so with pretty much everything, there's a little bit of uncertainty at least. So you give you a little bit of a range. Let's see. Use this exploration to identify the best method for dating bones of animals that are only a few thousand years old. Why is this the best device? So out of the 3 that we had, which one's the best one to use on bones of animals? Why? There's 2 reasons. Well, first off, do bones of animals have uranium or what was the other one in it? Yeah, rubidium. No, our bones don't have uranium and rubidium. So first off, because the carbon's actually in the samples for the animal bones. Second off, the animal bones aren't that old, and the half-life of carbon is a better fit to age things that are relatively young, because the half-life of carbon is going to be smaller than like the 47 billion years that rubidium is, which is crazy because that's older than the entire universe. Everybody's typing furiously. Okay, imagine you measure the abundance of parent atoms and daughter atoms in a sample and find that there's almost the same number of parent and daughter isotopes. What does this tell you about the age of the sample? Explain your answer. So that's going to be over here. Which one of these, 1, 2, or 3, is going to have roughly the same number of parent and daughter isotopes?
1.
1. Because what does 1 have? You have 50% of radioactive stuff. So if you have 50% radioactive stuff, what do you have in non-radioactive stuff? 50%. So it's 50-50. That's going to be a 1-to-1 ratio. So that's going to tell you that whatever the sample happens to be, you only have 1 half-life that has passed. So it's 1 half-life old. However many years that is, they don't tell us that. But what are we on here? This one? Yeah. What does that tell you about the age of the sample? That it has 50% has turned into daughter isotopes, and you only have 1 half-life old.
Wait, where are we putting number 6?
That 50% of the parent atoms have turned into daughter atoms, which means it's only 1 half-life old, which should tell you the exact date of it if you know what element you're using. But the 1 half-life is the most important part. Why is it important to have some idea about the relative age of a sample before radiometric dating? They kind of already asked us that because you want to choose the right radioactive element. If you're trying to date something that's very old, you don't want to choose a like carbon-14. There's not going to be any carbon-14 left. You want to choose a radioactive element that fits with the relative age of the sample so you get the best reading possible. Okay. Okay, and we kind of mentioned this in the last class. When Gage was here, he kind of asked about it a little bit. Why is it important to be careful interpreting absolute ages of clastic sedimentary rocks such as sandstone? Does anybody remember what's the problem with sedimentary rocks and aging? What are sedimentary rocks made up of? Layers, but specifically, like, what are the little pieces? Well, there can be fossils in them, but like a sandstone, where do the little pieces of the sand come from? Yeah, other rocks. And that's the problem. A sedimentary rock is going to be made up of pieces of other rocks that are going to be older. And so when you try to date a sedimentary rock, you can't really know exactly what you're dating. Like, are you dating a little piece of the older rock? Are you dating the younger sedimentary rock? Has water been through it? It's been at the surface for a certain amount of time. There's all sorts of problems. And so sedimentary rocks aren't really used for absolute ages because they're made up of pieces of other rocks. And so you never really know what age you're getting out of that. Last two. So excited. Ooh, all right. This is actually going to be a little tough. Identify 3 assumptions that radiometric dating relies on. Okay. I'm going to say these out loud and then I'm going to check and see if they're right. 1, I think the assumption is that all of a specific type of radioactive element is going to decay at the same rate. So when we have that half-life, we assume that it's going to decay at that rate. So half of it's going to go away when you have that time frame that passes for your half-life. I think 2, you're going to assume that it's a sealed sample, that it's not contaminated. You haven't had more radioactive elements put into it, and you haven't had any radioactive elements taken out of it. And then 3, I'm trying to think of 3. Let's see, will this tell us down at the bottom? The age of the Earth. Bill Nye should have told us yesterday. Weathering silicates. Let's go back to the top and try this. No, can't do that. Absolute age, fossil succession, radioactivity. Structure of atoms. I don't think it's in the atom part. Isotopes. I don't think it's in the isotope part. We're basically going with isotope stuff. Maybe it's in this part. Some isotopes are unstable. Half-life.
Okay.
Sample problem, solution, radiometric dating. It's probably in here. So why is radiometric dating important? So yeah, we're assuming, I already said that, we're assuming it occurs at a constant predictable rate so that your half-life is going to be the same for all the atoms of that same element. Different isotopes, different time scales. Got the times. Let me talk about the age of the Earth. I don't know. Just put those two so that your decay is constant and your sample is not contaminated. It hasn't had any more radioactive stuff put in. It hasn't had any radioactive stuff put out. I don't know what the third assumption would be. Someone wants to Google it. That'd be nice. 3 assumptions of radiometric dating. So let's see. What's number 10? Number 10, final answer. Carbon-14 decays to form nitrogen-14. Nitrogen-14, however, is a gas and can therefore escape from the sample. The sample meaning a dead body. Over time, because of this, we cannot calculate the age of a sample by measuring the carbon-14 to nitrogen-14 ratio in it. We use a slightly different method instead. If we did use this ratio to calculate the age, how would this calculated age differ from the actual age? Explain your answer. So look, let me turn the lights on for this one. If in a normal sample, we're looking for this parent to daughter ratio. So like I have a sample here, and I have circles for my parent, and then I have X's, mean the parent has turned into the daughter, and I have that ratio. I count them up, I get a ratio. Well, in carbon-14, the daughter is nitrogen, so it's a gas. And the gas is going to escape your dead body or the log or whatever it is. It's not going to stay in it. So in that sample, am I going to have any daughter atoms inside? No, it's all escaped, right? So it's all going to be just the parent atoms inside. And if it's all 100% parent atoms, what does that tell me about the age? So if this, as I go along this scale, I get older and older and older because my parent atoms are decaying into daughter atoms. What happens if I haven't had any parent atoms decay into daughter atoms and I'm starting at 100%? What does that mean for the age of the sample? It's young, like it literally just formed, like yesterday, and nothing has been able to decay at all. And that's not right, because we know it's been alive for it's been around for a certain amount of time. It's just all the evidence has kind of escaped. And so that's what they're kind of asking there. If we did use this ratio to calculate the age, how would this calculated age differ from the actual age? It would be much, much younger than the actual age, because all of your daughter atoms have escaped out into the air and blown away. And you wouldn't have that ratio to kind of confirm that. So nice. I think that's it. Let me see real quick if I can Google search the 3 things. Huh? The age would be much, much younger, because here I get this ratio and I'm able to say, all right, it's 1 half-life or 2 half-lives or 3 half-lives. If it just looks like I have 100% of the parent, it's going to look like it's extremely young, like it was formed today or yesterday, which actually is not the truth. What's up? No, you need to be going in between classes. I got to go out to 7th period because somebody wasn't using their restroom breaks correctly. 3 assumptions of absolute dating. Assumptions of radiometric dating. Every radioactive element will decay at a constant rate. I said that. The rate of decay is specific to a particular radioactive element. That's kind of the same thing. When the substance containing a radioactive parent was first formed, there was not daughter elements present. Ah, that makes sense. That's probably the one I missed. System has been closed. Yeah, that's what I said. All daughter atoms contained were created by the. Yes, so that makes sense. So basically, that is your third assumption. So the first one was everything's going to happen at the same. It's going to decay at the same rate for every single different type of that atom. The second assumption is it's a closed system and you haven't had any contamination. I haven't had radioactive stuff put in or radioactive stuff taken out. But for example, and let me flick this back over just so I know y'all can see. If my parent isotope is like uranium and it's turning into lead, which is Pb, I have to assume, if I'm counting the ratio between parent and daughter, I have to assume there was no lead in that rock at the very beginning, or I need to figure out if there was lead in that rock. If there was a whole bunch of lead in the rock, that's going to throw off my ratio and throw off my age. And so that's a third assumption.
Wait, so how do we write that in?
Assume that there was no daughter isotopes in the rock at the time of formation. Okay, and yeah, that was long and complicated, but we kind of worked through it together. So for Mr. Yang, would anybody like to say hi to Brandon Yang? Wave to Brandon Yang. He's the last online student in this class, so this video is specifically just for him. And if you have any questions, please email me. And if the rest of you didn't get a chance to finish or you missed a couple answers, the video is posted on Google Classroom. There will be a link to my YouTube channel where you're not required to like or subscribe the videos, but they are there for your educational purposes. So have a good weekend.